So there's one announcement for the practicals for the week 5. You have to come during week 4. So same timing, but I actually postpone a bit, 9 o'clock. So we'll start at 9 and finish at 12 or earlier. So next week, Monday, for your control module only. So you can see I put a bracket over there. Week 4 for group 1 and group 2 to come during week 4. So meaning that week 5 for control, there will be no practicals on week 5 because I'm not around during week 5. So your week 5, Monday, no class. We will be having Wednesday, the class online for the simulation using the Simulink. So now better you download or install the MATLAB before week 5 to check whether you're able to run or not. You can actually refer to the slides for week 5. You test run a bit for your MATLAB. So the MATLAB is like step-by-step guide in the PDF, in the slides. So you can test run your simulation. If it is working, then you wait for me for the Wednesday online session to run the simulation together. You test run a bit. Let's say you cannot use, or it will take some time to actually open. So for Wednesday class, you better turn on or open your Simulink first, because some of the laptop may take some time to actually run the simulation. Okay, so if you're in campus, then you can go to our usual venue there, also can. Okay, if you from home, then you can use your own laptop, so install. So if you are in campus, you want to use the computer PC, also fine, because we do have the venues for these simulation classes. Just I won't be there. You'll be having the online section in that venue. If you want to have the week 5 and week 6 in campus, you have the venue. You can check your timetable. Okay, the second announcement will be about your test. Your test will be, let me record the session. So record. Okay, so the first announcement will be the week 4. Okay, your week 4 lab is going to replace your week 5. So week 5, no lab. You come on week 4, Monday, 9 o'clock. So announcement already in my times. And also you can refer to the grouping. I already revised the grouping. So you follow the latest one in my times and also in the Telegram. So the group 1 and group 2 will come next week, Monday. So the Friday one, the week 5, we do not have any practicals. And then second announcement is please install your MATLAB and test run whether you can use the MATLAB or not, the Simulink. Then the Monday, week 5, we do not have class. I already posted in my times there already. Just announcement as a reminder. So our class will be on Wednesday, and it is an online session. If you are in campus, you want to have a venue to run the simulation, you can go to the computer lab. We already have the venue for that 2 weeks. You can go there. And then the third announcement will be your test. You can refer to the announcement there. Our test is week 7, and I'm using the Wednesday, I think Wednesday slot from 12 to 1:30. Okay, for 3 questions. So that one is week 7. And the fourth announcement, so we have 4 announcements. The fourth announcement will be your assignment topics already released. So you may refer to the My Times for the assignment 1 and assignment 2. So assignment 1 and assignment 2, the components will be individual components as well as the group components. So they won't be like an assignment totally group or totally individual. No, it will be assignment involving group components, meaning that you will be having half of the 20% for assignment 1 belong to individual. Same goes to your assignment 2, half of the 20% will belong to the individual. So you can refer to the rubric. What are the components belong to individual? What are the components belong to the group? The title of the assignment 1 and 2, they are the same. Just the scope are different. You may refer to the assignment 1 and 2. I will go through the assignment 1 and 2. Yes, Eamon, any question? You can just unmute and talk. Yes.
Miss, I just want to ask, our test on week 7, is that online or physical?
Physical. It's a face-to-face. You refer to the announcement.
Okay.
So I will be having a venue for that. I will update the venue to be confirmed. Now the venue I still cannot get from the timetable group, so I need the venue. Then I will post in my time. But for all the tests, even though it is an online class for lecture and tutorials, for all the modules, I don't know the safety lah. They will be actually face-to-face tests. Okay. So week 7, you have to come for the week the test. So the test only 10%. Okay. So the grouping of the assignment, I will form the groups. I will release the grouping by this week. But meanwhile, you can go through the assignment topics first lah to have a glance. So there are 4 announcements over here. So just in case you forgot. So number 1, so week 4 will be your PCI lab for group 1 and group 2. Okay, number 2 will be the week 5, Monday, no class. Okay, and then for your MATLAB, you have to install your MATLAB and the Simulink. So your class will be on Wednesday and it is online. Okay, online for lecture 5. So this all group under number 2. Number 3, your assignment already posted. Assignment 1 and 2, refer to my times. And 4 will be, what else? The number 4, your test. Yes, your test will be week 7, Wednesday. And it is a face-to-face for 1.5 hour. Okay, so yes, this is the 4th announcement. So 1, 2, assignment 3, and your test is 4. Okay, so there are 4 announcements already in my times. So I just go through all these announcements. Please take note. Okay, and it's recorded as well. So now, today is lecture 3. It is again the same learning outcome modeling. So last week we already learned how to model the process using the transfer function. So we derive the unsteady state balance, either it is energy component or it is the composition balance minus the steady state, and then you introduce the deviation variables, and then you Laplace transform both sides, rearrange output over the input, and you get the first order transfer function. Then we stop there. So this week, when you get the transfer function already, last week we only cover first order. So first order transfer function. So last week we have the k over tau s plus 1 as your transfer function g. So as response. So if you want to solve this question, you actually need to refer to the Laplace transform table to get everything in t response. Okay, t response, meaning that maybe it is a ke negative t over the tau example. So we actually stop when we already derive the first order transfer function. So continue from that. This week we are going to have second order transfer function. Second order transfer function will be k1, k2, combine k, then you'll be having tau square s square plus 2 damping factor tau s plus 1. So this formula, you check I think I actually provide this in the list of equation. So the list of equation, so for list of equation here. So this is the one you will actually get during your test and also the final exam. As you can see, it is actually given. So this is the, we call it as a default equation for the second order transfer function. So this is the equation. So this k is a combination of k1 multiplied with k2. So this is second order. So you can see from here, the first order actually is not given. So first order transfer function, standard equation is not given. So you have to memorize this, which is a simple one. K over tau s plus 1. So the second order default equation, standard equation for second order transfer function is given. Okay, so from here, you will be having second order transfer function formula provided to you. and this is the damping factor. So something like this, you can, or you prefer to write something like this, or you prefer to write something like this, it's fine. So damping factor, you follow the one actually there is something ding 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 like this. So as long as there's a curve, then it is a damping factor lah. So up to you to write the damping factor symbol. Similar to this. Okay, so the tau is the time constant that we have learned last week. So this is a tau. If you have a smaller tau, means the process is faster. So when the tau is smaller, means it is a faster process. Okay, when the tau is bigger, means the process is sluggish. Meaning that when you apply a change to the system, it will take longer time to achieve the steady state. Then we say the tau is bigger. Then we have the damping factor. So this damping factor we will discuss is like a new performance index to check how the process responds to a change. So we have some maths involved as well in this lecture 3 that I also put some additional topics. Actually, you have this heavy side learned in your maths too. So I have included the lecture slides and also some tutorial questions from your maths 2 last time. I have posted to my times. So that one for your revision to go through the heavy side again. Okay, so you will have heavy side learned today as well. So and the tau is here. So this is the second order transfer function. So we go back. So the outline for today also we will actually study when you derive the first order, then what happened? Okay, is it a fast process? You are going to actually get the T response and also sketch the graph, for example, to know the dynamic change. Okay, or we call dynamic behavior. Dynamic behavior is your function of T versus the time, the change of your output over the time. So this is the dynamic behavior. We are going to learn the dynamic behavior of the first order, and then next week we are going to learn the dynamic behavior of the second order. But we will derive the second order equation transfer function first. Okay, so this is the lecture outlines. So second order dynamic system, for example, how can you get the second order transfer function? For example, 2 tanks in series. Like this example, you have 2 tanks in series. Series means side by side. So if outlet flow rate from each tank is linearly related to the height of the liquid, in that tank, transfer function, they ask you to derive the transfer function of Q2 over Qi, which is the output of this process. You have 2 tanks over the input of this process. So we call this as the transfer function of the output over the input, Q2 over the Qi, means the final output over the inlet, which is the Qi. So you will get Q2 over the Qi. So why it is in uppercase? It is because you already Laplace transform both sides, change them into S response. Then you will get the small letter Q2. When you Laplace transform this, okay, like for example like this, right? You'll be having Q2S, Laplace transform. After you perform Laplace transform, you will get this. Means this is after Laplace transform both sides. Okay, and also they want you to derive H2, which is this one, over the input of the second tank. So it is a H2 over the over the Qi, no, the input of the first tank. They ask you to derive H2 over the Qi. So this is the transfer function they want you to derive. Okay, so we will be having this example. So this example you are going to derive if you have a piece of paper or you have the iPad or tablet, then you can derive this using the same steps that you have derived exactly like the last week one. You start with the unsteady state mass balance. So unsteady state mass balance is dm. So this is the unsteady state mass balance. It is because the question does not involve composition, does not involve temperature, only the volumetric flow rate. So this will only having the mass balance. So mass balance is dm over dt. So we will do for tank 1. Okay, after we finish the tank 1, we'll perform the same for the tank 2. Do the unsteady state mass balance for the tank number 1. So it will be W in minus W out. So it involves the change of level. So it will be rho A dH over dt. So tank 1 will be A1. And then the level of tank 1 is dH1 equals to rho Qi. The in we only have this one, and the out I have this. If the relationship is not mentioned, by default it will be H1 over R1 equals to Q1. Linear relationship. Okay, which means the higher the tank level in the tank 1, the faster the Q1. So your Q1 is H1 over the R1. Linear relationship. So you'll be having minus rho Q1, and your Q1 you will replace with the H1 over R1. So rho H1. So H1 over R1, rho A1 dH1 over dt. Okay, then you can cancel the density. Okay, it will become your first equation of unsteady state mass balance. Then you change this one to steady state mass balance. You'll be having A1 dH1s over dt equals to Qis minus H1s over R1. Then you'll be having equation 2. We actually repeat the same thing like we have studied last week. So from here, you'll be having equation 1 minus equation 2. Okay, so I will go through the example with you. So this one is actually starting for dm over dt equals to rho qi minus rho q1. Then straight away they expand this to become rho tank 1 is, you put here, this tank 1 is A1, tank 2 is A2. The cross-sectional area is given, meaning that the size of the tank 1 and the size of the tank 2, they are different. That's why you have the A1 and A2. Okay, so it is the same derivation like the tank level. We have already learned this rho A1 dH1 over dt last week, where we expand rho equals to m per v, m equals to rho multiplied with the volume, and density multiplied with area multiplied with the level. Then for tank 1, then we'll be having rho A1 dH1 over dt for the accumulation term. Okay, then they cancel the density. Okay, you will get this equation. So you need to go through again this one, derive again. So I will use the slide to demonstrate. So from here, this is the valve. So you can put a note there. If you have a valve, then you highlight here. This will be the linear relationship. To explain, the higher the tank level in tank 1, the faster the Q1. Therefore, the equation is H1 over R1 for your exit flow rate Q1. So this is the valve. When you have a valve, there will be a resistance to flow, meaning that you will make the flow actually slower due to this valve. There will be a resistance to flow. Follow the formula of H over the R. The higher the resistance of the valve you are using, the slower the flow rate out. The higher the tank in tank 1, the faster the Q1. So therefore, it is proportional to H1, then inversely proportional to the resistance. So H over the R. Therefore, you substitute this into Q1 to get the equation of the one we have derived. So you can put it here, this is H1 over R1. Okay, develop transfer function for tank 1. Okay, so how we already learned, we do not derive this from beginning, like assume tau equals to A1 R1, but we actually proceed to actually derive the whole thing until the end, and then we rearrange the equation so that it fulfills the pattern of the first order. Then we identify what is our K and what is our tau. So in this case, I will have, let me increase the page. So let's say just now we already have the equation of Qi minus H1 over the R1 equals to, so I put my output at here, A1 dH1 over dt. Okay, then our steady state equation, you already derived just now as well. So in the slide, they do not derive for you, they give you the final answer. So this is your equation 1, this is your equation 2. And you already have your VAF equation, which is Q1 equals to H1 over R1. Okay, so if you Laplace transform Q1, example, you want to Laplace transform this, you will get H1S over R1. Example. Okay, so from here, you'll be using equation 1 minus equation 2, meaning that A1 dH1 minus H1S divided by dt equivalent to Qi minus Qis, then minus H1 minus H1S over the R1. Okay, repeat the same as a revision. We'll do the full one for this question. So we introduce derivation variables. For example, I use the capital H1 indicates H1 minus H1S and Qi equivalent to Qi minus Qis. If you prefer to use H1 prime and also Qi prime, also okay. Fine. That's why you have to introduce which one you use. Okay, and then this equation will become A1 dH1 over dt equivalent to Qi minus H1 over R1. Okay, we repeat the same steps. We Laplace transform both sides, and then you rearrange the output over the input. So the output over the input for the first time, the output here, it is the H1, and the input is Qi. So this will be the H1 is output, and then Qi is the input. So you are going to derive H1 over the Qi after you Laplace transform both sides. Okay, so from here, you will continue to derive, you have to Laplace transform both sides first. So Laplace transform both sides, you will get A1 outside, then S, H1S minus H10 initial condition, and then equals to Qis minus H1S over R1. So we do not assume the tau from the beginning, like the slides solution. We'll derive until the end and get our tau equals to A multiplied with the R. So we do not memorize what is our tau from the beginning. So from here, for the transfer function, we already know there will be no initial condition because the steady state value will be exactly the same value when time equals to 0. No time to respond. So at time equals to 0, the value will be exactly the same, just like the steady state value. Therefore, this will give you 0. So from this case, when you rearrange, you will be having what's my last? So A1. So A1, H1, S. Move all the output to the left-hand side. So you'll be having H1S over the R equals to your input Qis. Factorize your H1S. You'll be having A1S. Okay. So just now I have the S over here. So multiply. S is missing. So A1S. So I have the A1S. Okay, so A1S plus 1 over R, and this is R1. R1, correct, okay, R1. Hang 1, because this is 10, so this is R1. Then equivalent to input. So output over the input will give you, so this one move to the top. So before you move, you actually can simplify this one first. Like the maths, you have the A1 R1S plus 1 over the R1 H1S equals to QIS. That's why your H1S over your QIS will be R1 over A1 R1S plus 1. Same as the standard equation of the first order. The last term here, take note, it must be equivalent to 1 and already in 1. So you don't need to modify anything. And by comparison, your R1 is your K, and also your tau is A1 R1 solved. So this is the transfer function for tank 1. Then you repeat the same for tank 2. You will get exactly the same one like H2S over the inlet for the tank is Q1. Okay, so this one will give you Q2 equivalent to H2 over R2, linear relationship. So you don't need to derive again because they follow the same equation, just tank 1 and tank 2 having different inlet. So for tank 2, the one going in is Q1 and here is R2 and here is Q2. So follow exactly the same. Your input is Q1. So this will be your input. Your output is H2. Then equivalent to R2 over A2 R2S plus 1. If you derive the first one, for the tank 2, don't need to repeat. You just apply the same, change accordingly. For the tank 2, the inlet is Q1, so we change to Q1. And the resistance to flow is R2, level is H2, cross-sectional area is A2. Then you already get your equation number 2. So just now, we have derived, I put it here, you have your tank 1 equals to Q, where's the exit flow rate of tank 1? Exit flow rate of tank 1 is Q1. So your Q1 is H1 over R1, and you have derived Q1S equals to H1S over R1. So this is for tank 1, valve 1. For tank 2, valve 2, you will get exactly the same duration, but this exit flow rate is Q2S equivalent to H2S over R1. So you have this equation. So altogether, you already have 4 equations. The one I highlight here. So 1, 2, and then 3, and then 4. You are going to use the what they call this rule. I think either it is product rule or chain rule that you have learned, so that you can derive finally the equation for the one they ask. For example, they ask for these two, 1 and 2. Okay, so you copy all the equation again that you have derived. So we summarize the equation to be number 1. You have derived H1 over Qi. You have derived H2 over Q1 as well. Okay, you have derived Q1 over H1. Okay, for example, your valve, right? You have Q1, so valve number 1, so if you look at the figure over here, so this is valve number 1. Where's my pen? Okay, I use this. So this is valve number 1. You have derived the equation to be Q1 equals to H1 over the R1. Okay, so you will be having the equation of Q1 over H1. And also, okay, you'll be having these 4 equations. You rearrange, you copy the 4 equations you have derived. Okay, then you'll be having also Q2 over H2. So these are the 4 equations I have. Okay, for the valve, H2 over Q2. Q2 over H2. Okay, so this one is just maths. Why you need to rearrange the position? Because later you have to know we are using the product rule or chain rule, something like that. So you have learned this in maths already. For example, okay, see, they ask you to derive this Q2 over Qi. you have to utilize all these four to finally get this. So what we do is we will focus the one on the top. You'll be having this, correct? So you will be having Q2 over H2 multiplied with this one on the top. So you will find something what is H2. Your H2 is only this. So H2 over Q1. Then you'll be having this one on the top, Q1 over H1. And finally, H1 over the Qi. Okay. So that you can cancel, and finally get this one over this one. This is you have learned in maths. I don't know which maths. So when you have this Q2 over the Qi, then you will start from top Q2. So Q2, you find which one relate to Q2. Like for example, we derive the equation, the one I highlight in yellow, right? So you have to find what is the Q2 equation involving Q2. Only this one. So when I only have this equation, like the one I put in yellow color, 1, 2, you cannot see what point. So this one, 1, 2, 3, 4, right? You have to find something have Q2. So only this equation have Q2, man. But you have to rearrange so that the Q2 will be on the top. So you'll be having Q2 over H2, right? You cannot rearrange Q2 multiply with R1, ma. Therefore, you will only get this one, ma. Q2 over H2. You have derived first, then you link to the chain rule how to actually finally derive the Q2 over Qi. So how we start? We will start with the one on the top, okay? This one you do want to memorize also fine. You use your maths. This is the question they ask you to derive Q2 over Qi. So you start with Q2 and put the Q2 on the top. Then I will go to this slide. Okay, I have this Q2. My Q2 must be on the top, means I must rearrange the equation to become Q2 over H2. Must be a transfer function, ma. So Q2 over H2 equals to 1 over R1. Then I will put it here, my equation. Then my H2 is at the bottom already, ma. So I must multiply with H2 on the top so that I can cancel out later. So H2, you go to find which one have H2 in the equation. So H2 over Q1. So H2 over Q1 is this one. Okay, then you find Q1 must be on the top. Then this one, Q1 over H1. Then you can cancel the Q1. Then H1 must be on the top again. Finally, it's H1 over Qi. So something like you can cancel to finally get Q2 over Qi. Product rule or chain rule, something like that. Then you put all the equation there. You have derived this. The equation for the first one is 1 over R2 multiplied with R2 over A2 R2S plus 1 multiplied with 1 over R1 multiplied with R1 over A1 R1S plus 1. Okay, so you cancel. Finally, we'll get 1 over A. We'll put all the information for tank 1 first and then tank 2. That's why this one will be placed at the front. So A1 R1S plus 1, then A2 R2S plus 1. Okay, so this is exactly like the pattern of K1 tau S plus 1 multiplied with K2 tau S plus 1. So 1, 2 to get this. Like your tau 1 is A1 R1. Then your tau 2 is A2 R2. Your K1 is 1. Your K2 also 1. You split into 2. Okay, so this one will be your second order. So when you have this, it is like the maths. You have tau 1 S plus 1 multiplied with tau 2 S plus 1. When you do the expansion, you'll be having tau 1 tau 2 S squared plus 2 damping factor tau S. So this one is actually before you compare with the standard equation, you'll be having tau 1 plus tau 2. You do the expansion, S plus 1. So this is the one we highlight, this one. When you do the expansion, but I do not use the A1, R1. I represent tau 1, tau 2. So tau 1 is A1, R1, tau 2 is A2, R2. So from here, this equation, you will compare with the default equation, which is tau square S square plus 2 damping factor tau S plus 1. So this is the standard equation for second order. Okay, cannot see this one. Okay, so from here, you have derived the second order transfer function for this one. Okay, so the answer is they derived for you already at this slide. Okay, so finally, you'll be having your tau 1 is A1, R1, and then your tau 2 is A2, R2. Okay, then you can derive your equation H2 over Q1, and then they want the Q2 over H2 as well. So from here, what else they want you to derive? So you can play around with the chain rule and derive the rest. Okay, so then we go to the next example. What if the tank 1 and tank 2, they do not give you the schematic diagram, but they give you the blocks. So this is like a series arrangement. Okay, so this is the block. The output of this block is H1. Input of this block is Qi. So if you want to derive the transfer function to represent the first block, it will be H1S over Qis equivalent to K1 over tau 1S plus 1. Let's say this is the second example. And for this block, it will be Q1 over H1 equivalent to the transfer function K1. And for this block is H2 over Q1 SS equivalent to K2 over tau 2S plus 1. And the last one, Q2 over H2 is equivalent to 1 over K2, example. So from this case, if you want to have Q2 over the Qi, it is just a multiplication of the first transfer function, multiply with the second, multiply with the third, multiply with the fourth to get the answer. So it will be H1 over the Qi, multiply with Q1 over the H1, multiply with H2 over the Q1, multiply with Q2 over the H2 to finally get the answer of output Q2 over the Qi. So this is how we get the transfer function of the final output over the initial input Qi. Final output Q2, initial input is Qi. How you get the answer is multiply all of them. Okay, multiply all of them. Okay, then you will get this one. You will do the expansion, smiley, chung, 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 to get this. And compare this with the standard second order equation, tau square S square plus 2 damping factor tau S plus 1. And this is given. This is a second order transfer function. So then by comparison, your tau square will be tau 1, tau 2. Then you can solve your tau equivalent to tau 1, tau 2 square root. Then your 2 damping factor tau will equivalent to tau 1 plus tau 2. Then you can solve your damping factor equals to tau 1 plus tau 2 divided by 2 tau, where you get your tau from here. Okay, so this is where you get your tau. Your tau, your tau. So this is where you finally can solve what is your tau and also your damping factor. So you are going to solve your K. So your K by comparison is 1. Then your tau you can get from the square root of this. And then your damping factor you can get from here. So by comparing the derived transfer function of the second order to its default equation, you solve three things: K, tau, and also damping factor. Okay, so this is when we talk about the second order transfer function, you have to calculate the K, the tau, and also the damping factor. Okay. So the solution is given here as well. So finally, you actually want to solve the K, the tau, and also the damping factor. Okay, so the K over here is actually K1 multiplied with K2 lah. Combine K, and you already solved the tau just now. I already demonstrated this one, done. And then 2 damping factor tau equals to tau 1 plus tau 2 because you compare. Like for example, you do the expansion already, so you can compare just like this slide lah. You compare with its standard equation, this one. Then you're able to solve all this. The solution is given as well in this slide. Okay, so just now, this one you already solved tau, where you solve your tau based on here. So you just sub in. This is your tau. It's the same solution like I have presented just now. Okay, so this is introduction, how we derive the second order transfer function. So how can you get the second order transfer function? Is when you have 2 tanks. Okay, 2 tanks. If you only have 1 tank, then you will get the first order. If you have 2 tanks, then you will get second order. Okay, so next. Okay. So second order system, we already have the standard equation given. So this one don't need to memorize. Second order, you just need to memorize the S response, K over tau square S square plus 2 damping factor tau S plus 1. The one in T response, don't need. Just like the first order, the one in T response, or D equation, we don't need to memorize. You just need to memorize the transfer function for the first order, and the transfer function for the second order is given in the list of equation, which is this one. The T response, you don't need to memorize. Just like the OD equation, this one, actually you don't need to memorize. They just explains to you, this is a tau, this is the damping factor, the Y is your output, and then the X is your input. Exactly the same like the first order OD equation. Okay, so this is in T response. What you need to know is just the transfer function for the second order. This one, you need to apply. It's given. So this is given in the list of equation. The one you need to memorize only the first order transfer function, which is K over tau S plus 1. Okay, next. So for second order system, you don't need to know this T response. So we already covered this S response already. So now you have transfer function block number 1, let's say represented as G1. Second transfer function is G2. So if you want to get Y2 over U1, which is the output over the input, it will be a multiplication of these 2 blocks. Means G1 multiplied with G2. Then if G1 is given, G2 is given, so they use the GP1, let's say GP1 and GP2. GP1, GP2. So your GP1 is K1 over tau 1S plus 1. Your GP2 is K2 over tau 2S plus 1. Then you do the expansion. Then you will get this equation and compare. You rearrange to get the output, which is this output. This is the input. So U1S, you will get, do the expansion, then you will get exactly this equation. And move this U, 1 is missing, so 1 here to the left hand side to get this. Then you will get K1, K2 over tau 1, tau 2 S square plus, this one wrong a bit, tau 1 plus tau 2 S plus 1, compare with your K over tau square S square plus 2 damping factor tau S plus 1. And finally, you will solve the answer to be tau 2. This equals to this equals to this, and this equals to this by comparison. So this will be the answer. So this is like you compare this one with this, then this whole thing with 2 damping factor tau, and then your K1, K2 is like your K. Then you will get this answer. Okay, so this is the introduction for second order transfer function. Okay, the general form for T response unit. Okay, then we will skip the T response or the equation. Okay, now is you link to the second week that we have derived the first order transfer function. So the first order transfer function general equation is K over tau S plus 1. Okay, so this is the output over the input. For example, they use the equation input is U. Output, I don't know what they use the symbol. So let's say it is, okay, never mind. So this is actually output over the input. So input, sometimes they use X, sometimes they use the U. So this is the input transfer function. So from here, there are different types of input that you can apply to this system. For example, you increase the input from one value to the second value, different value, and remain at the new value forever. Means there is a value change. One, you have to wait the process to become steady state first. Then you apply a change to the input. The change, there are many types. We only learn the popular types change that you can apply to the system. For example, we call unit step change. The change is by 1 unit, or it is a step change. Then it can be a magnitude of M. So it can be an impulse change. And one of it you have learned heavy side. It can be a pulse, rectangular pulse change. So we will cover this one soon. So they are representative of type of changes that occur in plants. For example, the simple example that you have the QI, and this is your level change, and this is the Q1, and it is H. Let's say it is a linear relationship, so it will be having the equation of H over R. Then you derive your equation, mass balance. You will be having your H over the input QI, SS, equivalent to K over tau S plus 1. This is a transfer function of the first order. So this is your input. What are the changes you can apply to this QI? You change the QI from one value to the other value and remain constant at the new value. This is the change we call as the step change. If you change the QI, follow the pattern like every 1 minute I go to increase by 2 units. Then another minute I go to increase 2 units. So this is the one we call as the ramp input. Ramp input means the equation will be, for example, 2t, like the one I explained just now. Every 1 minute you go to increase by 2 units. So for example, the time, the unit I use minute. So every 1 minute, 2 units. If plus, then it is increase. If minus, then it is decrease. So if this is a change, it is something like you have learned, it follow a slope like 2t. Means every 1 minute increase by 2 units. Another 1 minute increase by 2 units. So this is like 2t. When you change to the t response, your QI is follow the pattern of QI equals to 2T. Small letter means time response. Uppercase means already Laplace transform, QIS. So in T response, it follows the pattern of 2T. For example, this one is ramp input. Okay, so we will cover few popular. They are the representative of the type of changes that occur in the plants. So the first one is step input. So just now is introduction. It is like you have the equation of this one. You apply a change to your input, which is QI. So you can use this example, you can link back the. So this is the process. The output is H, the input is QI. Now, what are the of change you can apply to QI? The first one, you change the QI using the step input, means QI initially steady state may be a value of 50 liter per minute, example, okay? Then already achieved steady state, you go to change this QI to 70. So for example, 50 to 70. So I use liter per minute, example, liter per minute for my QI. So this is actually in time response. QI as a function of t, time response is 50 changed to 70. So if you Laplace transform, this is QI function s equals to 20 over the s, because it is a constant. The change is 70 minus 50, so the change is by 20. So if you Laplace transform 20, you have learned if you Laplace transform a constant, a number, you will get that number over the s. So you will change everything to capital QIS. So this is a magnitude of m. So that's why step input means I change my QI from its steady state value to a new value. If I decrease, then you will get negative. If I increase, I will get positive. You change by a magnitude of m. So when you Laplace transform, you will get m over the s. So let's say you have ut, it is m. So when you Laplace transform, you will get capital, you will get m over the s. So let's say I use the input QI. Okay. In the same example I provided just now, I use a tank level. My input to the tank is actually the QI. So I apply a change, meaning that my QI initially already steady state at 50. Then I go to change this QI to 70. So when you Laplace transform, it is actually Laplace transform a constant number, 20 over the s. So m over the s when you have a step change. So in 11th term, step change is you go to change the input by a magnitude of m. So when you Laplace transform magnitude of m, you will get m over the s. Okay, so this is the example. When the second example is the heat input to the stir tank heating system is suddenly changed from 8,000 to 10,000. So this is a magnitude of m. You use 10,000 minus 8,000, you get 2,000. So when you Laplace transform 2,000, you will get the answer of 2,000 over the s. When the change is a number, from one number to the other number, you Laplace transform that number will give you m over the s. Just like you have learned in maths, when you Laplace transform a constant, a number, the solution for this, the conversion, will be that number, the change, over the s. Okay, so this is the one we call as the step input. So when people tell you step input, okay, step input is actually from a number change to another number and remain constant. So when you Laplace a number, you will get that number over the s. Number is m, magnitude over the s. So this is the step change. Okay, second change is the one we have discussed just now, is the ramp. For example, it changed by a constant slope. Every 1 minute, the change is by magnitude of a. For example, it can be changed by 2, changed by 4 per minute. If let's say every 1 minute change by 10 units, then it will be 10. So if we want to put T response, so let's say I use my same example. This is my QI. This is my h. I derive my transfer function hs over qis. My qi, there will be two, one in time response, one in s response. So in time response, every 1 minute example or 1 unit of time, it can be 1 minute, 1 second, 1 hour. Let's say I use 1 minute. So every 1 unit of time, okay, change by, for example, A units. So you'll be having, if I follow this one, right, T response will be small q, qi function of t equals to at. When you Laplace transform this, you will get qis equals to a over s squared. So you don't need to memorize this. It is in the list of Laplace transform. When you have t, Laplace transform is 1 over the s squared. If you have at, when you Laplace transform this, you will get a over s squared. So this is the one they call as the ramp, or you can put general form is at. So this is like a function of t. And now using the same example, your qi is the one you have. So it is actually qi equals to at. Then you have qis equals to a over s squared. When you Laplace this, you will get this. So I don't put it too many things there. Then you can relate better. We can, okay, like this. So this is Laplace. When you Laplace transform, change it, then this will give you this. So what is ramp input? Ramp input is you have T response, you have S response. T response is AT. S response, T response is A over S squared. Okay? So AT means every 1 unit of time, you go to change by unit A. Let's say every 1 minute, you go to change by 5. Like after 1 minute, I go to increase 5 units more. So it will represent using the equation of 5t. So we can put it 5t means every 1 minute or unit of time. It can be minute, it can be second, it can be hour. Okay, increase 5 units. Okay, so this is AT, ramp input. Okay. Then you can put it here. So what is ramp input? Ramp input in T and in S. So in T, it is AT. In S response, it is A over S squared. So this is ramp input. So how to actually understand better, you go to put some notes there. For example, every 1 minute, the change is 5 units. Then I will having this one 5t. This one will be 5 over S squared. Okay, just like you are the operator, every 1 minute you go to increase 5 units. If let's say this is temperature, now it's 20 degrees Celsius, you go to change to 25. After 1 minute, it becomes 30. After 1 minute, it becomes 35. Change of 5, increase. It can be negative, means decrease. Starting from 30, drop to 25, drop to 20, 15. So this is actually the ramp input AT because it follows the constant pattern. Every 1 minute, you change the same value. So this is ramp input. So it will follow the slope. You just have to understand this and put some notes there. Then you will know when people tell you about the ramp input, it is actually every same unit of time, 1 minute, you go to change the same value, same units. 5t, every 1 minute, change 5 units. After 1 minute, go to increase another 5 units. So this is 5t. When you Laplace transform 5t, it will give you 5 over S squared. So this is the one we call as the ramp input. Ramp input. That third one is the hardest part, which is the rectangular tiles. We will go through exactly the solution, how you get finally this one. It is a long calculation. I will explain further during the tutorial section. It is a long calculation, but you have learned this in your maths too, using the equation of ht minus c, okay, and then ft minus c, Laplace of this, you will get e minus cs dot fs. We will actually solve this one again using some scenario application so that you will know how to link the Heaviside. Heaviside means the change is by a number. Just like now is 5, I go to change to 7. Okay, after 3 minutes, I go to change the 7 back to 4. So it is follow the number. A number change to a new number and then change to another number. So if let's say it is a rectangular pulse, initially, for example, it is 10, you go to change to 15, then you go change back to its original value. So the change is like a box. Originally 10, go to increase by 5 units, then go back to its original value. So this is like a rectangular. So we call it as the rectangular pulse. Initial value, after the changes, final value is exactly the same like the initial value. So this is the rectangular pulse. You will get this answer. It is not just memorized to get this answer. It is a long calculation from this part. Then you will get the answer of this part. We will have examples. Okay, you have to master the skill how to derive the rectangular pulse. We will have this one covered during the tutorial. Okay, so the solution is not given over here. What you need to prepare for the tutorial 3, go to do your revision. Refer to the additional notes for Heaviside already posted to my times. Okay, so during the tutorial 3, I will just go through the solution because I'm not teaching the Heaviside again. That's why the prerequisite materials already posted to my times. Please do your revision before you come to the tutorial section. If not, you will feel very blank, very fast. Okay, so do your revision to prepare yourself better so that you actually know how to solve the Heaviside. Heaviside means when you Laplace transform, you get function of s. When you reverse Laplace transform, you will get the function of t. So if you can still recall what you have learned in Heaviside, the idea of Heaviside is the solution of the Laplace transform is either it is 1 or either it is 0. So if it is 1, it is on. When it is 0, it is off. So we will cover this in our tutorial later in a more detailed way. Okay, so now, next. So, or after the class, I will show you one example. So let me finish all the changes first. So impulse input is when it is a very quick and the value is a number. So it represents a very short and transient disturbance. Just like you go to change the value to a new value. Yeah, it is wrong already. I faster change back to its original value. Maybe it is within 1 second. It is very fast, very short, and then it goes back to its original value. So it is just a very small disturbance. So the change, maybe it is 1, then it is 1. If let's say the change is 5, then it is 5. So it follows exactly the same value. When you Laplace transform, you won't get any 1 over the s or 5 over the s. So this is the impulse input. It means the change is very, very quick. Okay, so very, very short, then the impulse is 1. If let's say you change by 5 minutes, then the answer is 5, for example. Okay, and then you have the sine wave. For example, now your same, this is the H, and this is the one going in QI. So when you Laplace transform, you will get the HS over the QIS. Follow the same solution, unsteady state mass balance minus the steady state balance. Introduce the deviation variable, Laplace transform both sides, rearrange output over the input. So similar step, you get this output H over the input QI. So now the change is your QI now follow the pattern of, for example, from initial value 2, change to 5, go back to 2, change to 5 again. It is like up and down, up and down, up and down. The change applied to this QI is up and down, follow a sine wave. We'll cover this not so soon. You'll be learning this when you cover the topic of frequency response. When you want to derive the equation to represent your controller. So not so soon, but one of the input, it is a sine wave. Okay, sine wave applied to the Q. It is like the pattern of up and down. So these are the 5 popular changes of the input that always occur in the plant. Okay, now disturbance type also the same. You remember when we have these, let's say you can having actuator to control your QI, means your QI will be classified as manipulated variable because of this control valve. Let's say I have my Q2 here. My Q2 is just a flow into the system. If anything goes wrong for this Q2, I cannot do by adjusting. I cannot do anything because I do not have the valve to adjust the Q2. Then my Q2, they will finally affect my H. Actually, both Q1 and Q2 will affect my tank level. But Q2, I do not have any control valve. Therefore, my Q2 will be classified as disturbance variable. And my H here will be my control variable. Manipulated variable is anything not the desired value for the H. You go to change your QI. For example, the tank level is too high. You go to reduce the QI by adjusting the valve of this one. Okay? But you cannot change the Q2 because Q2 do not have any valve. It's a stream going in. So your Q2, it is the disturbance. When you derive, we have already tried this example. Finally, you will get addition class where you're having a transfer function of QI, then a transfer function of Q2, this one S, equivalent to your output, for example, HS. We have derived this, I think, last week or the first week, I can't remember. Meaning that, for example, I have my this one A, this one B. I have 2 equations. One is H over A. This one, output over the input. So first input is QI. I also have H over the Q2. So this is the transfer function. So transfer function. Because I have 2 inputs that affect the output H, therefore I will get 2 transfer functions. So if you have 2 transfer functions, how you identify which one is manipulated variable is identified which one having control valve. If you have the control valve, then it is manipulated variable. The other input do not have control valve, then it will be classified under disturbance. So the change for this example, my Q2 is the disturbance. The reason, because no control valve. Anything goes wrong to H, you can adjust QI, but not Q2. Will Q2 there no valve? So it is classified as disturbance variable. So if a change is applied to this Q2, it is the disturbance types. It is exactly the same like the 5 types we have learned. It can be unit, ramp pulse, unit impulse. So this pulse is like the rectangular, which means this one. And this we will learn more during tutorial. You have to solve using Heaviside. So you need to prepare yourself to go through the Heaviside notes, your previous maths too. So you will need to prepare before you come to the Wednesday tutorial 3. Please go through the Heaviside. So the materials you can refer to my types. So this is the disturbance. I have a link the example. Let's say your output is H. This output is affected by 2 inputs. One is QI, the other input is Q2. So you identify the one having the control valve, then you will classify the QI as your manipulated variable and your Q2 as disturbance variable. Then you have 5 different types of changes you can apply to this, which are these 5. Okay, so this is just something similar with the change you can apply to your manipulated variable. Okay, now once you have your transfer function, first order transfer function, you have the k over tau s plus 1. And let's say your input is generally represented using X, your output is generally represented using the Y. So let's say I have the same example just now. I have the QI and this is my H. My output is H, my input will be QI in S response. So now generally I use all the output, I use Y to represent my output and X to represent my input. So let's say you have your first order transfer function as this. You already know your input have 5 types of changes you can apply. It can be step input, unit step input, size, impulse, pulse. These 5. So we cover the first one. Let's say your input, it is a magnitude of M. So this is the one we call as the step input. Step input. The change is by magnitude of M. So if you use this example, your QI is initially at 50, already achieved steady state. Now I go to change this 50 to a new value 70 and remain the same value at 70. So the change is 70 minus 50, M is 20. So let's say during steady state, my QI is 50 liter per minute. Apply a change, which we call this change as step change to QI. QI now becomes 70 liter per minute. This is function of T. So when you Laplace transform, you will get QIS equivalent to 70 minus 50 over the S. So 20 over the S. So this is a scenario. So when you put this one, generally input is X, then you'll be having XX is M over the S. Then your input, so X is the input, equivalent to this example is QI. This example is QI as a function of S example. So this is the input. When you have an XT, the change is by M. M means it is unsteady state minus steady state value. For example, 70 minus 50. So this will give you the answer of 20 over the S. So when you have YS, let's say here, they are not using SS, they use this as an input. Refer to the question, it can be any alphabet they prefer to use. Sometimes they use the R, sometimes they use the U, sometimes they use the X. So sometimes the input can be the popular alphabet they use for the input is U, R, and X to represent the input. But they will tell you like this one, they represent the input using the alphabet U. Okay, now your US is M over the S. So you multiply this one to here, you will get M over the S. Means you will have this one. When you have this, you have to always think like S response has no meaning. You have to always inverse Laplace to get the equation of T response. How? You refer to the Laplace transform table, Km over S, tau S plus 1. You will get this answer. So you'll be having Km, which is this one. Similar, right? Let me check. You will get K, then M, still got one S multiplied with tau S plus 1. So Km over S tau S plus 1. Inverse Laplace of this. So you have to find something S multiplied with. So you will get this. Km S tau S plus 1. Inverse Laplace of this, you will get K is the constant, so don't touch. M also a constant, is a number, don't touch. Then you'll be having 1 minus E negative T over, follow this tau. So this is the direct conversion using the term 13. It's the same answer given in the slide, km bracket, then 1 minus negative t over tau, using a direct conversion of this. So this originally is output over the input, k over tau s plus 1. Now your input, it is actually step input, where you're having us equals to m over the s. So this one will give you ys equals to km over the s bracket tau s plus 1, because you just multiply this one to the other side. By checking the closest term, similar pattern, you will identify term 13 to do the inverse Laplace transform to get back the answer in the form of t response. So when you get the t response, when you plot the graph, you will get your output is your yt over the time. For the exponential term, you will just sub the t equals to 0 and t goes to infinity. Then you can further plot the graph to get the dynamic behavior, of this. So this is the example when we have the change of the input is step input. So this is the answer that you actually got it by referring to term 13. Okay. If you just refer to the written slides with no recordings, I think you maybe cannot know the flow of calculation, but I won't put the recordings forever in my Teams. Please do your weekly revision. I will remove the recordings. I'm not supposed to share the recordings for year 3 modules. I will share a while for your revision purpose. But if you think I will keep until the end of semester, no. So what you can do, maybe you can download lah. But when you download, it's for your own usage. Don't share to your juniors, okay? You pay for this recording, you know? Don't share with your junior. They should come for the class to get their recording during their semester. And most likely there will be different lecturers teaching maybe. So the recordings you download, you don't share to your friends, okay? Or your juniors. You keep all your recordings for your own usage. You are not supposed to share anything to your juniors lah. They will have their learning process. You have your learning process. If you share, you do not encourage them to be independent. You're actually helping them to become weaker. So I want the student to become stronger, so they need to struggle a bit lah. Don't help them. So this is the one where we're actually having, for example, they ask you to plot the graph. Example, the question asks you to plot the graph y over y infinity. Y infinity is when you sub the time equals to infinity over this t over the tau. So example, you will be having 2 parts. So one is your t and the other one is y over y infinity. Okay. So you already have your y here. So when the time equals to 0, so you can put it here. So what is your y at time equals to 0? And what is your y infinity? So y at time equals to 0, you can sub it here. You will have y0 equals to km 1 minus e negative t0 over tau. Means you will get this one 1. So 1 minus 1 will give you 0. You will get y0 at answer of link. So it's a 0. So this one is 0. You sub the t. Okay, when you sub t goes to infinity, you will get this answer equals to 0. Then you will get the answer equivalent to y infinity. You will get km 1 minus e infinity. You will have km because this will give you 0. Then you will have km. Therefore, you get y infinity is km. Then for t equals to 0, your y over y infinity will be 0 over km. So the answer, when you have 0, divide with any value, it will give you 0. This is your first dot. Then you repeat the same when this one done. So t equals to 1. So you sub y1 equals to km 1 minus e 1 over the tau. And then your y infinity already same value, you get km. Okay, so you will solve if let's say you know the tau value by plotting the second dot, third dot, and so on until the end. So because the tau is not given, so you can solve further. Let's say you can also try your t equals to tau. When your t equals to tau, you will get y over y infinity will give you the answer of 0.632. You can try later using the same step where you use this equation to find y, the time is tau. Then you will get the answer of 1. You can stop and get the answer. The idea is the same. So finally, you will get this value. You try later, 0.632. And this explains a very important concept. Tau definition can be defined as time taken to achieve 63.2% of the ultimate change. Look very hard, right? So when you plot the graph, when you have a change something like this is the ultimate change. I use delta y. This is the time. This is the yt. Let's say you have this. What is my tau? Let's say the total change is 10. The tau should be 0.632 times the total change of y. So at this point, I will be using 6.32. So this is how we get the tau. It's not equal. Solve tau. So it's not equal here. You remove the equal here. This is to solve. How to solve the tau? It's using the concept of 0.632 multiplied with the total change of delta y. You will get 6.32. Let's say the change is 10. If you want to link, you can link to the same example. I use a tank. This is my QI. This is my H. I'm having my output H S over QIS, something like this. So when you inverse Laplace, you're able to get your, when you inverse Laplace this, minus 1, you will get HS. Sorry, HT. Okay, inverse Laplace, you will get HT, which is, in this example, it is your output YT. Okay, when you apply a change to your QI, you're causing a change to this level from initial value to final value. Ultimate change is the final value minus the steady state value. So this YT, delta Y, is the final H minus steady state value. Okay, so I will circle this one. Let's say initial tank level is 2. After you have made a change to this QI, let's say you increase the QI, you make the volume metric flow rate entering the tank become faster, then the tank level will increase from the initial value to the final value. So the initial value to the final value is the ultimate change. 63.2% of the ultimate change, let's say the change is 10. So I will put it here. This is the value of 6.32. Then I go down here. This is the way I solve my tau. So when people ask you first order transfer function, how I solve my tau, is you have to plot the graph of the output versus the time. Then go to find the total change of this output delta y. Let's say it is 20. Okay, the total change from initial value until the final value is 20. So 63.2% multiplied with the 20, the answer is a value. So you will get this value to identify the tau. So this is how we solve the tau graphically. Okay. The time's up already for me to mark the attendance. Put your name later in the Telegram for attendance, because some of you sharing laptop. So please attend the class, please put your name later in the telegram who attend the lecture, because now already 4. I forgot for the attendance already. Okay, why no break? Why no one remind me to have a break in between? Now already 1.5 hours. So we have a quick break, 5 minutes, then we will come back. Let me see. We have another few more slides. I maybe need another 20 minutes. So yes. So we go for 5 minutes break. At the same time, please type your name in the telegram for attendance. I forgot. So we will continue this one later in 5 minutes time. Okay, I'm back. So let's say we use different example. You have a tank. Okay, now the inlet for this, let's say it is inlet entering concentration, Ca naught. The inlet stream, the concentration is Ca naught. And this contributed to the exit concentration. So your exit concentration is, let's say, Ca. Okay, this is actually using the equation of concentration multiplied with the volumetric flow rate to get the dm over dt. You have derived this in the previous example. We use the concentration multiplied with volumetric flow rate. Okay. So now they want you to study the dynamic behavior of your output, which is Ca, over the time. So let's say you have the equation, you start from the dm over dt. You can refer to the previous examples in previous lectures. You use the mass balance. Finally, you get your Ca over Ca naught as your transfer function. Okay, so this is the transfer function of output over the input. So now a change is applied to your input. Let's say this is the step change. It must be a step change. So let's say this is the question we have. We have a step change that applied to the inlet, which is the input. In this example, the input is Ca naught. So the step change, so you'll be having, once you Laplace transform, you're having m over the s. So in this case, you will get your Ca as a function of t, equivalent to just now, what's the equation already? This one, Km 1 minus e negative t over the tau. So Km 1 minus e negative t over the tau. Okay, then you sub the t equals to 0 until few values of t until t goes to infinity. You were able to get the blue curve of this blue curve, the change of the Ca over the time for the step input, first order transfer function. Okay, now how you find the tau? So we repeat the second time. The tau is the change of the output. So the change of the output we call as the ultimate change. So in this case, it is the change of output is Ca. Initial value, so using an unsteady state value, the final value, final, minus the steady state value of Ca during time equal to 0. So the total change of Ca, total change. If you plot already, it will be the initial value until the final value. So this range is the ultimate change of the output, which is the ultimate change of the exit concentration, which is this one. So initial value of the Ca, when a change applied to the input Ca naught, you wait for a while, collect the data until this Ca achieve another steady state due to the change you applied to this Ca naught. So the change from the beginning steady state until the end point steady state, the total change of this we call as the ultimate change of Ca. So 63.2% of this total change is where you actually solve. Let's say this is generally total change is delta, the change of Ca. So 63.2% is where you can find your tau, where this point is actually 63.2% multiplied with the total change of output. So this is total change of output. So if you have this example, like the tank example, this is your input Ca naught and the exit concentration is Ca. You apply a change to this Ca naught. Initially, it can be, for example, the unit for the concentration is kg per, for example, gram per ml. So this is the unit we have for concentration, gram per ml. Mass over volume, gram per ml. Let's say it is 5 gram per ml. You go to increase the concentration to 7 gram per ml. So it is 5 gram per ml, change to 7 gram per ml for your Ca naught. Okay, then you stand there, perform the laboratory works to collect the data of the Ca. When you increase the inlet Ca0 to a new value, this acid concentration follow your mass balance, it will actually affected by this Ca0. So you go to collect the Ca from initial T equals to 0, take few interval, then you slowly plot all the Ca until finally your Ca already achieve steady state. Perform laboratory works to collect the data of the change of this Ca. So this is the initial value. This is the final value. So from here, you will get the total change of this Ca multiplied with 33.2%. You will get somewhere around here. For example, the change is 1.8 lah. The initial value is somewhere around here, maybe 0.9, I'm not sure. So the total change of this multiplied with the 63.2% is this value, example, this value. Then you go down, you will get the tau value. So this is how we solve the tau graphically, okay, by performing the lab works to collect the data of the Ca due to the change you have applied to the inlet concentration Ca0. Okay, so another example is thermometer. So we have learned thermometer duration as well. We have the Y output to represent the thermometer reading and the surrounding temperature. In this case, surrounding temperature is this thermometer is placed inside a water bath. So the surrounding temperature is the bath temperature, water bath temperature. So in this case, if they only mention, okay, now you have the time constant, only one time constant is given to you, then it is a first order. If two time constant is given to you, then it is second order. If three time constant is given to you, then it is third order, and so on. Follow the tau. In this case, only one tau is given. Only one tau is given. So you are having K over tau S plus 1, which is the first order transfer function. So thermometer, they should tell you the output, let's say, is Y. Bath temperature, let's say it is X. So this is your input. So when you have Laplace transform, you will get YS over SS when you Laplace transform. So this Y stands for the thermometer reading, and this is the bath reading, the change. You imagine you have the water bath initially steady state at a value of 90. So you have two water bath. Okay, so this water bath, your X steady state is 90 degree, or you put the X as equals to 90 degree Fahrenheit. The water bath temperature initially steady state at the value of 90 degree Fahrenheit. So imagine if this thermometer comes into equilibrium with this water bath, the initial value for your Y during steady state should be exactly the same value like the water bath. So your water bath temperature, 90 degree F, also will be the steady state value of your thermometer at T equals to 0. So your thermometer should also give you during steady state or Y bar or Y0. The other is X0 at time equals to 0, steady state. It will be exactly the same as 90 degree Fahrenheit. So when everything achieves steady state, now a change is applied at time equals to 0. You place this thermometer into the second water bath, where the water bath temperature already achieved 100 degree Fahrenheit. So the change, now you remember transfer function, you actually use deviation variable, means it already represents the change. So in this case, your X change from 90 to 100. So if you change to Laplace transform, it is actually M over the S. it is 10 over the S. From 90 to 100 for your input water bath. From 90 change to 100, so it's a magnitude of 10. When you Laplace the X, so if I put function of T is actually 100 minus 90. So this is deviation. You must always minus the steady state value. Deviation means the value you change 100 minus the steady state value, so the change is the magnitude of 10. When you Laplace xt, which is 10, you will get the answer of, when you Laplace this, you will get the answer of xs equals to 10 over the s. So if 1 tau is given, you will get, if k is not mentioned, by default it is 1. Tau is 0.1 s plus 1. So this is a first order transfer function where they say the output is ys over the ss. Now your ss is 10 over the s. You multiply this one to this side, is exactly the same equation like ys over ss equals to 1 over 0.1 s plus 1. K is not mentioned in the question. By default, it is 1. If it is mentioned, you follow the number given. If it's not mentioned, it is 1. Okay, then from there, your ss is 10 over the s. Then you will get the answer of ys equals to 10 over s, 0.1 s plus 1, where the conversion is actually using the same term 13. You will get your yt equivalent to 10 1 minus e negative t over the tau, where tau is 0.1. This is your yt, where this is the answer. Okay, now the question says, determine the time needed for the thermometer to read 98. Y at time equals to 0, we can write in different ways. We can put ys is originally 90 degree Fahrenheit. Scenario is just something like this. Your water bath is 90 degree Fahrenheit. When you put your thermometer long enough, the time long enough, it will achieve equilibrium, meaning that your thermometer reading will exactly having the same value like the water bath. So at time equals to 0, your thermometer steady state value is the same as water bath temperature. So it is 90 degree Fahrenheit. So, or you call y bar. 3 ways: yt, y times 0, or y bar, or ys, the same thing. So it is 90. Now they ask you, how much, what is the time needed from this 90 to finally reach 98? So when you put in the t response, it is a value, right? So it is a deviation, means unsteady state minus steady state of y equivalent to 98 minus initial value of 90 equivalent to 8, right? Equals to all of this, you copy 10, 1 minus e negative t over 0.1. Your change, you cannot just consider final value. You have to consider the deviation. Final value is 98. What is the initial value? 90. Why is 90? Because the thermometer reading at the beginning will achieve the same value exactly like the water bath. So water bath is 90. When you put your thermometer in that water bath, you wait until this water bath, same temperature as the thermometer reading. Then we say already achieve equilibrium. Your thermometer will having the same value 90 before you apply a change to this water bath. So at time equals to 0, your water bath and thermometer reading should be having same value unless your thermometer is spoiled. If your thermometer is a perfect, accurate thermometer, the thermometer when you put in the water bath, and the water bath is set or controlled, fixed, maintained at 90 degree Fahrenheit, your thermometer will be having 90. When you wait until this thermometer to reach the value of 90 and remain constant. So that's why I put my initial steady state value as 90. It is because of your thermometer should achieve equilibrium with your water bath. Your water bath temperature is set at 90 degrees Fahrenheit. So initial value for Y at time equal to 0 is 90. Now the change is by 8 units, 98. So you have to consider this YT is a change, not final value. The change from steady state value 90 to 98, the value is 8 units. Then you use your calculator. You already know how to use your calculator. For this one, you can use the soft. For example, you type 8, then alpha equal. Your calculator something like, if let's say you have the calculator, same model as mine, FX570, you'll be having your alpha on the top. How can I see background? So alpha here. Use this. If you don't know, you YouTube a bit. It is actually using the equation of 8 alpha equal 10. Just type equation as usual, 1 minus e minus t over 0.1. Then you shift calculus 2 times. Shift calculus using a calculator, the top is shift ma. Then calculus 2 times. You will able to solve your t. So you don't do the maths like rearrange, then loan both sides. T finally 0.161. Utilize calculator to solve this equation using the function of alpha solve, shift solve. So this one is to solve without actually rearranging the equation. You can solve the t. So this t is 0.161. It's the time taken for the thermometer reading to reach 98 from its initial value 90. Okay, so impulse response. Now your ys, let's say it is the first order over the, I think they use the US, it is k over tau s plus 1. Impulse means it is a very short change, very quick, and the change may be by a unit of 1. When you plus 1, you will get the answer of 1 as well for impulse. When they say this is impulse, okay, the change is by unit of 1. When you plus 1, you cannot get 1 over the s. If you get 1 over the s, it becomes unit step change already. Like if let's say magnitude equals to 1, you Laplace the m, you will get 1 over the s. This is not impulse. This is a change we call as a step, a unit step change. Like 50 change to 51, 20 change to 21. The change is by 1 unit. This is unit step change. Impulse is different. Impulse is, the change is very short. Okay, so the change after you Laplace, it will be the same value as 1. Okay, so from here you have US equals to 1. You multiply to here 1, you will get back this value. This is impulse. Okay, so from here, meaning that your US is 1 when the time it is an impulse. The change is impulse. Okay, when you rearrange, you will get this. Actually, you don't need to rearrange. You can straight away 1 over tau s plus 1. You can refer to the list of equation, Laplace transform. So you refer to tau s plus 1, term 6. Okay, so you copy this. This will be your answer. 1 over the tau e power to negative t over the tau. So you don't refer to the, you don't follow the solution of the slide, but you refer to the term we have, which is term number 6. So I put here, this can be solved using term number 6. So don't need, straight away you can use 1 over the tau e negative t over the tau. Okay, so it is term number 6, 1 over tau e negative t over tau. Right. So this is your YT solution. Okay, so this is exactly when you multiply your tau to the other side, you will get tau YT equivalent to e negative t over the tau, exactly the same answer as this one because they multiply the tau to the other side. But we don't follow this. We use term 6, which is this one. Okay. So this is the impulse. Ramp impulse is, we have done this previously. So let's say you have your YS over the US. The change of your input, okay, is ramp input. So if let's say ramp input, you have time response, you have S response. So time response means your UT small letter is 80. When you Laplace transform become capital US, it will give you A over S squared. Don't need to memorize, it is actually term 3. Let's say you have 80 here, your answer should follow A over S squared. So this is term 3, ramp input. So T response is AT. S response is A over S squared. What is A? A means every 1 unit of time you change by unit A. Another 1 minute you go to change by unit A again. Another 1 minute you go to change by unit A. Positive means increase. If you get negative, it means decrease. So AT represent the change in the form of ramp input. If I go to change my temperature of this room, now it's 20. Every 1 minute I change by 2 units. So 22. Another 1 minute, 24. Another 1 minute, 26. So this is 2T. Change by 2 units per 1 unit of time. Unit of time can be minute, can be hour, can be second. So this one is 80. So this will involve partial fraction. You can try this. How you solve this? Let's say you have this, you'll be having S squared. So this is the partial fraction we have. You'll be having, remember, if let's say it is just S power to 2, we means this is the repeating roots. So you'll be having A over the S plus B over the S squared. You repeat 2 times, then plus C over tau S plus 1. Okay, just like you will get, let's say now you having your, this come from YS over SS equivalent to K over tau S plus 1. Now your SS is A, let's say they use a BT. In this example, they use, they use a B instead of A. So now we change accordingly. Your XT is ramp input and it is BT. So when you Laplace transform this one, it becomes B over S squared. So B over S squared, then this equation will become YS equals to B over S squared multiplied with the K. In this case, they put the they do not have the K. Yes, they do not have K. Let's say I assume K equals to 1. I'll be having S squared tau S plus 1. Then you'll be having this A over S plus B over S squared plus C over tau S plus 1. Solve using partial fraction. Okay, then when you put the S equals to 0, A over the S, B over the S squared. This one you can solve later, C over tau S plus 1. Solve using partial fraction. Or use the S equals to, how to make this term gone? It is when you put S equals to negative 1 over the tau. Then you have negative 1 plus 1 equals 0. Or you can have the other S equals to 0. And you can solve for the C as well. You put another S value. So this is how we solve using a partial fraction. When you solve S equals to 0, you solve the B equals to the capital B. Means you will get B equals to B. When you solve S equals to negative 1 over tau, you will get the B equals to C over tau squared. And I can't remember which value I put, but this is solved using partial fraction, so try. It's very simple using the partial fraction solution. then you can finally get this. When you get this, you refer to the Laplace transform table. So let's say I get this snapshot. Then I compare, oops, so clear page. So when you have this, the first term, b over s squared, will be as a direct conversion, you will get the AT. So you will get the answer of BT for this. Okay, and then the second one is B tau over the S, means you will get tau over the S. So which one tau over the S? Tau is a value, so you will get actually this tau over the S, you will get the answer of unit step. For example, it is you will get the answer of tau. Finally, is your inverse Laplace. You will get the tau. Then this one is, if you do not divide by tau, you will get just like the direct conversion. Solve using partial fraction, you can solve until the end to get the answer exactly based on this Laplace transform table to get the final answer of all this. And of course, this one you have to refer back. This is B tau. This one is term 13, I'm not mistaken. So factorize and so on. Try to get this exactly the same answer. Okay, but I give you some rough idea. It is solved using the partial fraction. So this example, you have to solve using partial fraction. And the change is RAM input. So when the question involving, the question actually, the input, the type of the change they are applying to the input is a RAM input, then you cannot run away by solving the final answer using partial fraction. So if the change is just the step input, then it is very simple. It's a term 13. If I'm not mistaken, it's term 13. So if it is term 13, yes. If the m equals to magnitude of m, so when you change the US, it will be m over the s. If the change is step input, the answer will give you term 13. If the change is RAM for your US, where you will get the answer of b over s squared, for example, or a over s squared, where you get the change is 2t, bt, or at, bt, or at. In this list, they use a, but in the question, they use the b. So if the RAM input is applied to your input, then you have to solve further using the partial fraction. Okay, so the example is given in the lecture slide. And then this is for your homework. Okay, so homework means we have learned this already, and we have solved this similar question using integration method. Lecture 1, I think so. Now the same question, but you solve using transfer function method. So meaning that for simplicity, we make the following assumption. Density and volume constant. When volume is constant, you have derived previously, you actually identify all the mass rate going in or equals to the mass rate going out. Like for example, W1 plus W2 equals to the W. You can derive again like dm over dt equivalent to W1 plus W2 minus W. Rho V dt. When you expand the m equals to rho, then you will be having dv over dt. So when v is constant, you'll be having this one equivalent to 0. When this is 0, then you will be having W1 plus W2 minus W. You can use during unsteady state and also steady state. So this is one. Okay, second, W1, W2, and W are constant. Before the change, after the change, they are constant at the same value. Okay, so what is the one they change? The one they change is x1. So x1 means your input. You have two inputs. Input 1, this is input 2. First scenario is vary input 1. and input 2, which is your x2, constant. Okay, transfer function is always we derive the unsteady state mass balance. So unsteady state mass balance is this one. So this is an unsteady state composition balance, where we use the equation of dmx over dt equals to wx of in minus the wx of out. Then you expand the equation of m equals to rho dv over dt, right? When you have dm over dt, because m equals to rho v. That's why you have this. And when you have x here, means the x is inside. But due to v is constant, then you can avoid the chain rule. You can have rho v dx over dt. And we demonstrated also when v is not constant, then you have to solve using the chain rule or product rule, like the lecture 1. So in this case, v is constant. Simplify the whole thing to be w1 x1 plus w2 x2 minus wx. And they say x1 vary, x2 constant, so you have to put the s here because x2 is constant, or in this case, you should put actually the bar on the top. So you derive the same, just like using the unsteady state equation minus the steady state equation. You should able to derive, like this case, they represent the deviation variable x prime. It is actually x minus x steady state, like this. Then same goes to your x1 prime is actually x during unsteady state minus x1 during steady state. So S. Same concept. So you can foresee the one-off question in your test. An instruction will be given to you. Either you solve this, you can compare the solution you solve using integration method and you solve using transfer function method. Transfer function method will be easier because it doesn't involve the initial condition. So that's why they say you can solve. So this is your homework. I will create a folder for this one for lecture 3. So this blending system is your homework. Okay, try to solve until you get this answer. Same goes to second scenario when both of the x1 and x2 vary. So when you have the x1 and x2 vary, then you will be getting the equation 2 transfer function. x1 and x2 vary means you have 2 inputs. When you have 2 input means you have 2 transfer function. Your output is, based on this example, your output is x. So you'll be having transfer function of x over x1. Output x over x2, function of s. You do not derive 2 times. It is just one single equation. You split into 2 parts. Like in this case, they are using a prime, 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 prime. You will get a long equation like this. So you'll be having first part and second part, and this is the output. You will move to the left-hand side. It is the same equation of the composition balance. Just finally, you will split into 2 transfer functions, just like the first one and the second one. You can see this is a long equation, right? So I split to x prime over x1 prime as this. Let's say it's A. This one is B. So I'll be having output x prime over x2 prime equals to B. Same equation split into 2. Output over input 1, output over input 2. Then you will get this answer. This is just half of the solution. You imagine the question continue by the test, values given to you. What you need to do is you actually have to go back to the Laplace transform table, and they have to tell you the change, the type of the change you apply to the x1. Step, ramp, rectangular pulse. So we will cover the examples of solution involving calculations when they tell you, okay, now the change of the x1 is changed from one value to a new value. So this is a step change. If let's say the change of the x1 make it harder, heavy side, change to a value from a initial steady state value, change to a new value, go back to its original value. So 2 times of changes, right? Let's say from 5 change to 7, change to 5. So it is like a rectangle. 5, 7, 5. Maybe for a period of 0 to 3 minutes, example. So this is the one we call as the rectangular house. We will cover this in the tutorial Wednesday. Okay, so the Wednesday we will have long tutorial for a few examples, important. So then week 4, we will cover second order dynamic behavior, the easier one, easier compared to week 1, week 2, week 3. 5 and 6 will be repeating the same one, but we run using simulation. Then week 7 will be our test. So this one is example 1. So try to solve all these. So you have 2 things to solve. One is getting the transfer function. Second is this example, you derive exactly the same one, but numbers are given in the question. So you have 2 questions. One is, can you derive this? Second, when I include numbers, like same example, numbers, can you solve further of these 2? So this will be your homework. The solution is given. I just want you to try again. Okay, so that's all for today. Yeah, overrun a bit. Solution is given. I just want you to try before Wednesday. And at the same time, please do your revision for your heavy side. Okay, you must know how to go forward and backward. Laplace transform of the heavy side transfer function and inverse Laplace transform for the heavy side, and only focus on the change of involving number. You don't change a function of t. You have learned in maths, right? The change can be analytically, for example, from time within this time 2 to 5, larger than 5, example. Last time you all learned, like for example, maybe function of t, 2t, maybe 0, for example. But our change is easier. It is a number, means it won't involve any function of t inside. So it is simpler compared to your maths form. That's why we call heavy side, meaning that the change involving only a number. From a number, change to another number and change back to its original number. Like 100, change to 110, back to 100. So if I want to put it here, it will be using division. Initial value, this one, let's say my steady state value is 100. So I should always 100 minus 100, 110 minus 100, 100 minus 100. So this will give me ft equivalent to 0, 10, 0. So let's say this is during 0 to 2, and this is larger than 2. So this is when t smaller than 0, right? And then the change of 10 is when 0 to 2, and this is larger than 2. So this is initial value. Why you get 0? It is because of no time to respond yet. So the value will be exactly the same value like the steady state. At time equals to 0, you'll be using the same value like the steady state value. So at time equal to 0, the value will be the same like steady state value. So you minus the steady state value will give you 0. So this is the one we will cover in the tutorial later. We call this one as a rectangular house. So the homework for today is only the last 2 examples. Okay, then you submit. Okay, I will go through. I won't discuss, but this one will be like something, the behavior of learning. Means when the time go to final, right? You let off few marks. I will I will refer to your behavior of learning. If I ask you to submit, you never submit, or you always submit late, then if let's say you let off 1 or 2 marks to get a better grade, then I will say you don't deserve because you never follow the instruction. Homework never submit, always absent for class. But if let's say your behavior is super good, every time I ask you to submit, you submit on time. You never absent for the class. This is something like the bonus marks. Okay. For example, you let off few marks to get a better grade. Okay, good student. Okay, I give you that 2-3 marks for a better grade. Because for every lecturer, we have like 5 marks in our hand. Okay, to give to the students so that the student will get a better grade. Not for me to revenge. It's for me to give you more marks for you to get a better grade. But let's say your attitude is not good, always never submit any homework I ask. You can see the homework is there for you to understand the whole lecture better. If you do not do, then you will struggle for week 3 tutorial. And as I said previously, your final will actually start from week 1 until week 14. You have to make sure you can follow well since week 1. So do your revision on weekly basis. Okay, that's all for today. Thank you very much.